So today, let's just go straight to it. Let me present the question for the day. So our question for today, we are solving this one. We'll be doing question 5. And on the question, we are given two functions, f of x and g of x. So f of x is equals to sine x minus 1, and g of x is equals to 2 cos x. And the functions there for the interval x should be between 0 degrees and 270 degrees. And then 5.1, we are required to sketch on the grid provided in the answer book the graph of f and g for the very same interval x being between 0 degrees and 270 degrees. Now, I don't have the grid provided on the answer book, but I can sketch the graph somewhere here. I can make it happen. By the way, the grid is that sheet that they give you at the back of your, when you're writing a final exam for South African students, you have that paper where you can do your drafting there. It's wiser to practice also so you can get your scaling right before the exam. But now here, whatever will be plotting here, it won't be according to scale as such. Now, welcome to Simplified RSA. We are the guys who makes it look easy. I'm Mr. Maimane. And then on today's one, this is how I want us to look at it, right? So before we sketch anything, when we look at the functions, right, we can see that from the standard form of sine, or rather from the standard form of a sine graph and the standard form of a cos graph, if you are familiar with those, we can see like here, there's a bit of a changes, which brings me to the so-called transformation of functions, right? Remember, we have different types of functions. We have linear function, where we can get the straight line graph. We have a quadratic function, where we can get the parabola function or parabola graph. We have hyperbola. We have so many different types of functions, but now we happen to be facing a trigonometric function, which is now we have the graphs for sine and cos. And by the way, I believe we all know the standard form of a sine graph, and we all know the standard form of a cos graph. But here there are changes. This one has been transformed. So because of the transformation, we have to now make the changes also on the graph. So now this whole thing brings me to the word transformation, because we're going to experience a whole lot of different graphs transforming in different forms. I'm going to give you my understanding of how I use, or rather how I track my mind to can picture transformation graph into any other transformation that I can think of. Let me take you through a story lane. It's not even a story lane. I just want to show you two of my favorite transformation in this lifetime. This one is not graphs as such, but it's two of my favorite transformation if you want to understand the whole concept of different types of transformation. Now, there's this one. Do you still remember the first time seeing Goku transform into the Super Saiyan for the first time ever after the fight with Frieza? That was the best transformation. But also, this one also is one of the coolest transformation you can think of. Cool, right? But at the end of the day, here, we can picture this as, so here, we have two events of transformation that happened. I want you to picture this same as functions or same as graphs. You're going to have graphs under paper 1, which is going to be your linear functions, your quadratic functions. And also on paper 2, you're going to have different graphs also, which is your sine, your cos under trigonometry. But then transformation is transformation the way we can picture it as it should be happening. Here's an example. Just to go back on a typical lane, a hyperbola function could be given like this, a over x, hypothetically. And we know that ideally, this is going to be something of this form. If it's 0 there, then it's going to be something of this form. sometimes this graph can transform and become something of this form. X is equals to A over X plus B, maybe plus C, something of this. So you gotta show the new changes there, that it transformed and moved to the new form, something of this form. So from here to here, ideally, the values would work themselves out. That is transformation of a hyperbola for in case. So now we have our two functions. So our standard form for a sine graph and the cos graph is going to be like this. So the standard form of cos and sine looks like this. So ideally, we should know that the standard form of a sine graph looks like that. And to get all the points here, we just punch in on a calculator. Sine 0, it's 0. Sine 90 is 1. And then 90 and 1, they interact there. Sine 180 is 0. Sine 272 is minus 1, like that. That's how we get the line. Also, the standard form of the function of cos looks something like this. So this is our standard expected sine graph, and this is our standard expected cos graph. Now, like I say, we do know the standard form of a sine graph as well as the standard form of a cos graph. In the situation of our question right now, we have f of x is equals to sine x minus 1. What does that mean in terms of the changes of the standard form of sine x? And also, we have g of x is equals to 2 cos of x. Now, what is the changes from the standard form to what we have here? So now we're going to discuss what really happens when there's a transformation of a sine graph or a cos graph, or rather a trigonometric function graph. But I'm going to use sine function as an example. So let me put up this image here. You can see that we have y is equals to a sine b, where we have x plus c inside the angle plus d outside. So all those are the possible changes that can happen from the standard form of a trigonometric function to that. So the a, as labeled in green, represent the amplitude. So if there are changes with the amplitude, meaning for the standard graph, the amplitude for sine x and cos x is just 1. So if there's any change on the amplitude, you can see how the shift is going to happen. So the amplitude affects the stretching of the graph, like it affects the stretching based on the y-intercepts. So you will see as we answer the questions, I believe. But then all those changes here, you can see, for instance, again, for the last one, plus D. Plus D shows a vertical shift also of the graph. But then it's more easier when we demonstrate than when we actually show the image, right? So let me show you from the standard form what's going to be our changes for these ones. So for standard form, we have y is equals to sine x, right? And now on our question, we are given that y is equals to sine x minus 1. And sine x minus 1, in this case, for our perfect transformation formula, we can relate to now is the cases of where d is added. But now, because it's a negative here, the changes is such that from the general function, the graph is just going to move 1 unit down. So from 0, the graph is going to move 1 unit down, and then our new 0 will be here. So the graph is just going to go like that, just underneath then. So everything is just going to move down like that. So our new graph, ideally, we're going to have something of this form. For the standard form of cos x, we have this graph, right? But for our case now, we have y is equals to 2 cos of x. So let me just write this here properly so I can have a space for drawing the graph. Y is equals to 2 cos of x. This is our new change from the standard form. So this affects what? It affects the amplitude. So generally we said our amplitude here is 1. Hence we have 1 and minus 1. This is our amplitude. Now, If the changes becomes 2, it means now this new graph now will have a new amplitude of 2 units. So it means now we must extend -2 and 2. So the amplitude is going to stretch like that. So meaning our new graph is going to be of this form. There goes our new graph. Nothing really changes, just that it changed the amplitude from 1 to 2. So if I extend it like that, it's going to go also like this. So this is our new, this is our new, this is our new sort of imaginary graph from the standard form. So y is equals to 2 cos x. It gives us this. Now we are required to plot this and this on one scale. So now let me put it like this. We all know this is f of x. And this is g of x. But also, when we plot our graphs, they don't want us to show the entire graph. We must only show from 0 up until 270. From 0 up until 270. So we must only show this part of the graph, only this part. We must not show the whole thing. So we're going to draft this into a bigger picture. Now let's have our final graph. I think this base can work. So our final graph will be, these are the y-axis, these are the axis. The entire time, these are the y-axis, x-axis, y-axis, x-axis. So now I've made it clear that I'm gonna search, I'm gonna only plot from 0, 90, 180, and 270. So I'm only plotting from 0 degrees, 90 degrees, 180 degrees, and 270 degrees, because it has been stated that x is between 270 degrees and 0 degrees. So they don't care about the whole part. So now this means that I will have this means that I will have -1 there and -2 there. And then I will have +1 here. I'll have +2 there. So now, taking this into consideration here, the function for g, it's going to be like this. That's the function for g. And the function for f is going to be something of this form. And then the function for g is going to be of this form. By showing this, moving from here to here and showing this is where you collect all your 6 marks. This is where you're going to collect all your 6 marks, because you have shown the graph of f, I can just show it there, the graph of x, and the graph of g, and the graph of g for the interval 0 and x. So you haven't exceeded 0 and everything is less than 0. You just show this part of the graph only. But then we moved from the standard form, and then we transformed the graphs, and then we plotted the same thing under one Cartesian plane like that. So this is how you do question number 5.1. Again, for a question like this, if you can manage to answer the first question of the graph with understanding and you understand exactly what you're doing, the next questions that follows is just a walkover. Let me show you. 5.2. 5.2.1, you have to write the amplitude of G. 5.2.1, you have to write the amplitude of G. And then for the amplitude of G, we did say like the amplitude is the changes of the number that is attached to cos. The amplitude is the changes of the number that is attached to cos. As we can see what amplitude is based on this diagram. So clearly the amplitude in this case is going to be this value here. So so this was the answer for 5.1. Therefore 5.2.1, the amplitude of G is 2. The amplitude of G is 2. 5.2.2. Let me just say amplitude. Amplitude of G is 2. 5.2.2, we have to determine the range of F. The range of F. Let's look at the range of X. The range of F. So if we're looking at the range, we're looking at the limitation on the y-axis. So the range of F goes from -2 up until 0. So the range of X, the range of F is that one there. So the way we represent it when we write the range, we're going to say the range of F is -2 Yeah, the range of F is between 0 and 1. So the range of F, y is greater than -2 but less than 0. Or you can just say y as an element of, and then you use, instead of brackets, you're going to use, what do we call these brackets again? So we use the box brackets to emphasize that both -2 and 0 are included because the range touches -2 and as well as 0 there. So for 5.1.1, for 5.2.1, the amplitude of G is 2, and for 5.2.2, the range of F, it ranges between -2 and 0. That's the answer. Like I say, after you answer 5.1 by showing up the proper graph, all the answers are going to yield themselves out of the graph itself. And then the next question, 5.3, we have to use the graph to determine the following. Number one, 5.3.1, we have to determine the number of solution for f of x equals to g of x in the very same interval between 0 and 270 degrees. Now, here's the thing. The solution where g of x is equals to f of x is actually where there's an interaction of the graph. So we can see the graphs interact there and they interact there. So there's two interactions of the graph. There's this interaction and there's this interaction. So two interactions means there's two solutions. So the answer to 5.3.1, to determine the number of solutions that are involved, you just say two solutions. That's it. It's two solutions because it's one mark. Yeah, you get your mark. Two solutions. We have this one here, this interaction here. We have this interaction here. Actually, you can actually determine the solutions, but then for now, that's what we care about. And the next question, 5.3.2, we have to determine 5.3.2. We are required to find the values of x in the interval 0, where x is between 0 and 180 degrees. So we're looking at x between 0 and 180 degrees from 0 up to here. Given that for which sine x is equals to 2x is equals to 2 plus 2 cos x. So 5.3.2, we have the situation such that sine x is equals to 2 plus 2 cos x. Somehow, we can see that this can be simplified to sine x is equals to 2 if I take a common factor, and then we have 1 plus cos x. Meaning in this situation now, we have a situation where at the range for G and F, because we have to find the solution using this graph, we can see that the solution for F and X, like, because of the range, in this case, the range goes from, we have to look between 1 and 1, but then even though the range for F is -2 and 0, but the range for G is -2 and 1. Now we are looking at the solution between the interval 180 and 0. So somehow looking at this situation here, that's when we can say X is equals to 180 degrees for the solution for this case here, because sine of 180 is 0, and also cos of 180 is -1 in that case there. So for the solution for this one, for 5.3.2, it's going to be 180 degrees like that. So like I say, the whole point was, if you can sketch the graph properly to answer all the questions that followed from here, it was very much easy. But also something to consider or to remember is that you'll always have different types of transformation of graphs, which is the main basic point. Mathematics has a lot of graphs. Join us as we do more questions. I'm Mr. Maimane. This is Simplified RSA, and we are the #1 learning platform because we are the guys who makes it looks easy all the time. And follow us on all our social media platform. Feel free to contact us if you have any question or if you want to inquire about our private lessons. And remember, we offer the first lesson for free. So to claim your lesson, please email us on info@simplifiedrsa.com. Otherwise, you can contact us here. I'm Mr. Maimane. This is Simplified RSA again, and we make it easy.